Earlier, I dropped a video about the I2C Driver board by X camera. In that video, I demonstrated the features of the board and how to use it with a serial EEPROM IC. Ultimately, I found the board to be very useful. See, I have an unnatural interest in taking sensors and modules and redeploying my own drivers to be used with unsupported platforms. For example, I once took an LCD character display with an I2C backpack to allow communication with an Arduino, and I wrote drivers for it to be used from the command line of a Raspberry Pi. Tools like the I2C driver board make it a lot easier to test the bitstream and commands for writing the driver. I can only imagine how much smoother the driver development would have gone if I had this device back then. I really did enjoy this tool, and I was really looking forward to seeing what the SPI driver board could do. Now, I did change the intended test module a little bit. I was going to use the SD card reader, but I don't know if I could find a more boring way to test this tool. So I went and bought a module that would provide more instantaneous feedback. And, of course, shiny lights. This is a simple OLED display from Vellemen. In typical Vellemen fashion, the datasheet for their module has sample Arduino code. But in typical me fashion, this display may very well never see an Arduino in its life. So let's look at the datasheet for the actual display and try to figure it out. Now, I really can't say this enough. Vellemen is very good about providing accurate part numbers. In this case, the display is an SH1106. And after downloading all 50 pages of the datasheet, I was greeted by about 10 pages of functions and the respective memory addresses. But for right now, I need to wire this thing up. Obviously, I need the power pins, so I connect 5 volts and ground. The datasheet does specify a voltage range for the display that would be more compliant with a 3.3 volt device, but this module was designed for an Arduino with a 5 volt logic level, and a quick glance at the back of the module reveals a linear voltage regulator. Curiously, this does seem to be the only real support circuitry, so it is realistically possible to directly connect a display to an MCU. Moving on, I can connect the clock pins together as well as the MOSI pins. The module does not break out MISO because I shouldn't need to pull any data from the display. And finally, I will connect the CS pins, allowing the bus to be enabled. With the device wired, let's take a look at what commands to send into it. Page 30 has a compiled list of all the commands and what bits are needed for them. If necessary, these commands have more detailed descriptions listed above the chart, but they are mostly self-evident. There does appear to be an extra pin needed though, that is not part of the SPI interface. The pin A0 seems to determine whether the byte sent is a command or display data, and is broken out in the module as DC for data/command. The SPI interface doesn't provide a means to toggle this extra pin. The driver board, however, does have 2 output pins that are not part of the interface. So I'll just attach the DC pin to output A. Admittedly, I'm not sure what the intended purpose for these extra pins was, but theoretically they could be used as alternative CS lines to allow for multiple devices on the same data bus. With the wiring done, it's time to play. Here at the bottom of the datasheet is a remarkably useful flowchart, the startup sequence. At first, I thought this flowchart specified what the display does upon power up, which means after power up the device is ready to receive and display data. So I pulled output A high to allow data writes and sent a few bytes down the pipe to see how it looks. Well, that didn't work. I was clearly missing something, so I tested the display on-off command. Maybe it never turned on. So I set output A to low and sent hexadecimal AF, and this fresh dose of torture came out. Looking at the flowchart again, I saw this step right here says setup initial code user setup. So maybe that suggests everything above this happens automatically and everything else is manual. For testing purposes, I kept the module in its default state, so on to the next step. Clear internal RAM. Checking the command chart for the byte that will clear the memory, it became abundantly clear there is no such command, which means the RAM has to be manually cleared. Fortunately, this device was just powered up before this, so there shouldn't be any data in memory. Moving on. Set display on. Once again, keeping output A low, I sent hexadecimal AF and this again. For the life of me, I'm not even sure what this is. There isn't a clear pattern to it. It's like RF snow from an old analog television. I guess the display memory is vulnerable to background noise when there's no power to retain a memory state. Or something. So the memory will have to be manually cleared on power up, not a problem. It looks like the memory is simply overwritten, so realistically I just need to replace each pixel with the intended value and redraw the display. And here comes an issue I have with the driver board. Each row or page of the display has 132 columns, 8 pixels deep. Every byte sent writes to an entire column, which means I need to send 132 bytes to write an entire page. There are 8 pages on the display, and they have to be manually selected and have the cursor manually reset back to column 0. Unfortunately, the driver board software, which looks just as beta development as the I2C board by the way, does not seem to support multiple byte writes, which means after power up I have to write 132 bytes, then send a page change command followed by a column change command, which means redrawing the entire display will take 1,140 bytes sent one at a time, or around 9,000 bits. Yikes. There is some hope, however. While the display memory is 132 bytes per page, the actual display is only 128 bytes. The first and last 2 bytes in memory are omitted on each page, saving 32 whole writes across the entire display, or approximately 2% fewer writes. You're welcome. Now, I am not the most creative person, so I'm just going to fill the screen with an incremental binary count, which will make a simple pattern or something. Given the 8-bit depth of the columns, it should take about 4 counts to completely fill the screen. Now to clarify, this will take me quite a bit of time to do, but a programmed MCU would blast through this. Take an Arduino. The SPI clock on an Arduino is typically capable of going up to 4 MHz. Dividing the 8,864 bits sent by 4 million cycles per second gives 0.002 seconds. So writing the entire display could take about 2 milliseconds. For some perspective, the human response time for visual stimulus is about 100 times greater. Now for the reality check, the SH1106 only supports a max frequency of 360 kHz. So the same 8,864 bits would actually take 24 milliseconds to write. Now that I'm finally done sending all the bytes, I can get a good look at the display. And actually, it's pretty fantastic. The pixels are bright and very well defined, and I could have a lot of fun with this display in other projects. Perhaps a review will be in order because there really is a lot more to cover as far as the display is concerned. About 40 more pages of the datasheet. But this video is about the driver board. This board is almost exactly like the I2C board. Except, as of recording this video, the software does not support multiple byte writes. I'm not sure if the software for either board is still in development because the interface looks fairly unrefined in both cases. Useful and powerful, but unrefined. I also know the developers have started at least one other project and may have moved on. This doesn't present a real problem, just a small inconvenience when writing an entire display. But the board is not designed to permanently drive a module. It is just a simple way to quickly test a bit stream for said module, and for that purpose it is exactly what I need. Both boards make it easier to test sensors and modules without having to program an MCU and still go through the requisite guess and check process. Also, just like the I2C module, I think this would really benefit from some form of protective case. Seriously, both of these boards are 80% screen and very thin. It would be absolutely easy to break these in general handling if you're not careful. Something this board has that the I2C board did not have is some extra power pins. It might not seem like much, but a problem I ran into with the I2C board was trying to test the very LCD display I mentioned earlier. The I2C board was a 3.3 volt logic level and the display was 5 volts. I could use a logic level converter, but I need to have both voltages to reference the converter. And this is no small task without readily available voltage sources. The SPI board provides 2 pins each of 5 volts, 3.3 volts, and ground, presumably to power the devices being tested. But these pins can also be a reference source for a logic level converter if needed, opening the board to more potential devices for testing. This has been fun. Before this project, I had never dealt with SPI so directly. Sure, I have the SD reader, but I always just use default libraries with it to write data for log files. I know, default libraries. I'm a monster. But what can I say? I had never touched SPI before this. And now that I've had the opportunity to explore SPI, I see the appeal of it. It's very fast. So let me wrap this up and summarize. The SPI Driver board is another welcome tool for creators. If you are someone who finds themselves dealing with a lot of SPI sensors in your work, definitely get one. Just like the I2C module, they are available from Adafruit and Crowd Supply, although I don't know how much longer the Crowd Supply listing will stay up since that campaign ended a long time ago. I'll make a video in the future exploring the OLED display in a little more detail, so keep an eye out for that to drop, and I'll see you all next time.